I'm going today to present TRUESET, a system for verifiable set computations. This is joint work with my advisors, Papamanthou and Elaine, and also with Dimitrios, Papadopoulos, Mahmoud and Nikos Triandopoulos. So cloud computing enables many applications where clients outsource their computations or storage to remote servers in the cloud. And this can be useful if the client devices have limited storage and processing capabilities. But from another perspective, this can result into different types of concerns. So from one perspective, you would like no leaks to happen in the data. You have privacy concerns. And this is addressed by a direction of research, like the oblivious trams, like as we saw in the previous talk, or processing of encrypted data, etc. Also, you may have integrity and correctness concerns, where you would like to make sure that the function that you are outsourcing is being done or carried out correctly. And this, for example, motivated research in things like proofs of retrievability and the subject of this talk, which is verifiable computation. So let me define verifiable computation very quickly. So it enables a client to outsource some kind of computation to some untrusted party in the cloud while being able to verify the correctness of the result through some kind of a proof that the server computes in order to enable the client to make sure that the operation has been done correctly. And in order for this to be really practical, we should expect the proof to be as small as possible, and as well the time to verify that the proof is correct should be small, and the proof computation time should be small as well. So it turns out, like based on the current recent research, like the first two objectives are, we are somehow there, but we're not there yet for the short proof for the proof computation time. And this is what we are going to try to address in this talk or in this paper, where we would like to reduce the proof computation time for an important subset of computations, which are set operations. So set operations appear in many different applications, like database join queries or different measures of similarity metrics. But it turned out that applying verifiable approaches for the set operations can be really expensive currently, and it can take more than 100 seconds to produce a proof for an intersection of 256 element sets. And what we do in TRUESET is provide much faster proof computation for set operations. And for this particular case, for example, we achieved less than 1 second in this case. And to give you a little bit of context about this problem, so the problem of verifiable computation has been there for a while. There has been different solutions that were proposed, like some solutions were based on secure hardware, other solutions were based on replication. But there is another direction of research who would like to rely only on cryptographic assumptions. And the solutions that were proposed in the very beginning in this approach were very unpractical until in the last 3 years there has been an impressive progress in this area. Multiple implementations have been produced. And well, I'm going to combine like some characteristics for these solutions. Like we are able now to do verifiable computation using a small constant size proof that's just a few hundreds of bytes, like it's 288 bytes for Pinocchio. And also the verification time is asymptotically very short. It's just order of the size of the input and output, but we still have a challenge with the proof computation time. And I'm going to describe very briefly now why we have this a challenge in these systems. So for a subset of these systems, the input is a file that contains the subset of the C language, and now there is a compiler that compiles this file into some kind of an arithmetic circuit, where each wire in this circuit carries a value in a finite field, and the gates of the circuits are multiplication and addition mod p. So imagine if your logic in the program gets complex or the number of inputs gets very high, the translated circuit will be very large, resulting into many cryptographic operations taking much time. And specifically, we found that the arithmetic representation of set operations is very expensive. And as the set cardinality increases, the proof computation time will increase very rapidly. And also you have another challenge here. Like in this figure, for example, you will see that each element in the set is represented by a single wire. This will add some limitation here, like because if you change the set cardinality, you will have to change the circuit, or you are going to assume a worst case scenario that you produce the circuits for. And also you have to assume the worst case scenario when you do a circuit like an intersection. Like when you do an intersection between two sets, for example, the output could be an empty set or it could be a full set. It just depends. These are the two extreme cases. And when you build a circuit for such model, you have to account for the second case, because this is the worst case that can happen in this case. So, and we would like to, in TRUESET, to help with all these challenges. So the goal is to reduce the proof computation time for set operations and achieve input-specific running time for the prover without worrying about the worst case, and also retain the expressiveness of the previous techniques. By the expressiveness here, I mean we want to be still able to run arithmetic operations and set operations in just a single program. And the way we do this, the main idea of this approach is, like, this is the perfect case that we want to see. We want to see a circuit that has a set per wire without changing the with changing the cardinality of the set. We don't want this circuit to change. And the approach that we use for this one is to build what we call a polynomial circuit, where each wire in this case carries a polynomial, and the gates is just multiplication and addition gates. And this is instead of the previous model where we had an arithmetic circuit where, as I just said, the disadvantages of this approach, where each wire in this figure carries a set element. Now, this is the main idea because, as you see in the set circuit, since each set is represented on one wire, it's changing the cardinality of any of the sets want to change the circuit. So now we are going to discuss how to do sets as polynomials. And for a set that's represented this way, like an n-element set, we represent it by an n-degree polynomial. It looks this way, where each element is a negative root of the polynomial. And just to give you a quick example how things now should look like, for example, if you have a polynomial intersection circuit and you have the inputs that you see in the figure, then you should expect the output polynomial to be the intersection of the two sets, but in the polynomial format. And also, like, if the two sets are disjoint, then you should expect a zero-degree polynomial on the output. So there are two primary advantages of this approach. As we're going to see, the circuit size will be constant for set operations, and also the effort will correlate with the degrees of the polynomials in the wires. So if you have an empty set represented by a zero-degree polynomial in the wire, your effort will be correlating with that. Not like the previous approaches where you had to account for the worst case. So now the question is how to build an O1 or constant size circuits for set operations. So as we have just seen, like when I have an intersection gate that looks this way, where each set is represented by a polynomial, we find that the output of this intersection set should be the greatest common divisor of these two polynomials. And when we have a polynomial that's the greatest common divisor of two other polynomials, then we have some properties that we can make use of here. So based on some properties, we will see that there are if and only if some polynomial is the greatest common divisor of two other polynomials, then there should exist four polynomials that achieve these four constraints. And as you see here, these four constraints can be represented in a very compact way in arithmetic polynomial circuits. And the important thing here is that no matter what you change, the degree or the size of the sets, this circuit size will be constant. And in order for the server to calculate these four polynomials, he can run the extended Euclidean algorithm for this. Now, I have to emphasize again that now when the server receives a query that he would like to do an intersection of two sets, now the server can do whatever he likes in calculating these two sets, but he will need just to prove to the client that he has some inputs that make this short circuit consistent. Also, we develop similar gates or like similar gates or for the other operations like the union and the difference. It works in the similar way. Like we also utilize the properties of the greatest common divisor and do or add more multiplication gates in order to get the union and the difference. Now we discuss how we retain the expressiveness of the previous techniques. So in real life, the queries may include both set operations and arithmetic operations in the same time. And for example, like in a SQL query like this one, you have a join operation where you would like to get the number of the elements in the resulting set. And this can be seen in this figure, like you have some part that you would like to run a set circuit, then followed by some part that you'd like to run an arithmetic circuit. And the way we do this, we propose some set of useful gates that enable us to transform between polynomials into typical arithmetic values. And without getting into much detail, we have gates like 0-degree assertion gate, which makes sure that a value on a wire is just an arithmetic value. We have also split gate, which splits a polynomial, or like splits a set represented by a polynomial into each individual element. And we have also useful gates like the cardinality gate, which can give you, or like tell you exactly how many elements are in a set. So far we discussed how to build efficient set circuits. Now, how to build the verifiable polynomial circuits protocol, how to enable the client to successfully verify that the server has polynomials making these circuits consistent. So we utilize here some concept that was proposed before, which is called quadratic arithmetic programs, proposed in Eurocrypt last year and used in Pinocchio. So if we have an arithmetic circuit like this, this can be seen as a group of equivalent constraints that looks this way. And in order to check for each of these constraints one by one, it will be really expensive. So what happens in this technique is that all of these constraints gets encoded into just one univariate polynomial. Assume there is some magic that takes all these constraints into just one polynomial. And the root of, or like, there are multiple roots for these polynomials that can enforce all of these constraints together. And in order to extend this to our approaches, or our approach, we have polynomial circuits. We do the same. We get the equivalent constraints, and we build a similar polynomial to before. But one important observation here is that the polynomial here would be a bivariate polynomial. And this required us to change the protocol and change the proof in order like, to account for the other variable that appeared in this polynomial. Now, the server, or like based on our protocol, we use the QAP to build a snark, a primitive called a snark, which is succinct, non-interactive argument of knowledge, and build our protocol, which I'm going to give a quick outline for it. So the protocol outline we have in the beginning, a stage where the QAP, or the quadratic polynomial program, is being used to generate what we call a verification key and an evaluation key. The evaluation key is used by the server to compute the proof. And after the server computes the proof, he returns the result along with the proof, and the client makes use of the verification key to verify the result. It should be noted that the evaluation key here is usually much larger than the verification key, because the evaluation key correlates with the size of the circuit, but the verification key correlates with the size of the input and output. Of course, we utilize some cryptographic assumptions and cryptographic tools, but you can refer to them in the paper. Mainly, we use bilinear maps with some cryptographic assumptions. All of the details and the proof are in the paper. So for the implementation, we added support to Pinocchio C++ implementation to handle verifiable polynomial circuits with loops. And we used open source libraries to handle the field and crypto operations, because these parts were not available in the released Pinocchio's implementation. And just some information, the operation is being done in a field whose prime is 254-bit prime, and the security level for the next result is 127. And we compare here with two Pinocchio's implementation. So the one that was released by Microsoft Research, and another executable that we built using the open source libraries that we used for TRUESET in order to have, or to ensure having a fair comparison. And in our comparison, we compare with arithmetic set circuits that does intersection and union and so on. And there were two variants to develop circuit programs in this case. So one way was to do a pairwise approach, where we use an order of n square equality gate. And also, like, there is a sorting network approach, where we combine the two sets, we apply a sorting network. Now we have the sorted data together, and we check for any consecutive elements in the output array. And for the set programs that we ran the evaluation on, we ran on a single union operation and as well multi-set operations, as you see in this figure. And the input sets contained random elements from the field. And it should be noted here that for each input set size, we had to generate a different circuit for Pinocchio, because, as I said, you have to always account for, each element in the set is represented by a wire. So we needed a different circuit for Pinocchio, but in our case, we used the same circuit again and again. Now, in the next figures, I'm going to show how the proof computation time enhanced under our approach. So in the case of the single gate, we were able, when the set cardinality is 256, we were able to get like 150x speed up. And for the other case, we had a speed up of more than 50x when the set size is 64. And this is also while achieving more than 90% savings in the evaluation key size, because if you remember, I said the evaluation key size correlates with the size of the circuit, and since our circuit is very small, then we were able to achieve much saving in the evaluation key size, and this is why retaining almost similar verification time and verification key sizes. So in order for us to get to these results, there were some optimizations that we implemented, like how did we do the bivariate polynomial operations, how we calculate the output polynomial, and so on. And also, like in the online version of the paper, we give a version of the protocol when the sets like reside on the side of the server. Like so far in our experiments, what we did, the sets resided on the side of the client, but in the real cases, we should expect the sets to be on the side of the server. So we proposed a protocol for that based on Merkle tree proofs. And it should be noted as well that TRUESETs provide an inherent support for multi-sets already, where you can assume that like a duplication of element inside the set is allowed, while other approaches will require more complexity. So the conclusion here is that we presented TRUESET, a system that aims to enhance the proof computation time for verifiable set computations. And the main takeaway here is that modeling set operations as polynomial circuit helped us achieve much better proof computation time and achieving great savings in the on the evaluation key size, while having an input-specific running time for the prover. Now, I know there's a question whether is this practical yet or not. So far, it is not. This is just one step towards trying to make cryptographic verifiable computation approaches more practical, but the results is not in terms of the current performance metrics, it is not yet practical, but there is growing effort and interest in these approaches in order to push them to be practical. Okay, thank you.
We have time for questions.
Hi, Murat Kantarcıoğlu, University of Texas at Dallas. I want to come to the practicality part in order to understand how much it scales. So in terms of data set size, what is asymptotic? Is it ON square type of proof computation? So as the sets increase, let's say ON size sets, okay, how does this proof computation scales? And also, how impractical it is currently? I mean, if I just download the data, do it myself, how much worse I am than doing this?
Okay, so for the complexity analysis of you'll find all the complexities listed in the paper, but generally, for something like the verification time is linear in the size of the I/O, which means that asymptotically it would be better for the client to outsource the computation to the server. But since the cryptographic operations are very constant, are very high, this will add the high constant to the complexity here, which adds more overhead to the operations. So this means that at a large number of set elements, you're going to see an improvement. But for the small set sizes, the native execution time will be much faster. We have we wait for more enhancements in order to get to this case, or to improvements in this case. Also, for your second point, in real situations, we should expect that the client is not keeping the data sets on his side. We should expect that he also outsourced the data to the remote server. And in this case, this is why we proposed a protocol that helps us with this, because assuming that the client have all the input sets and sending it to the server may not be very practical. This is why we have this modified version in the ePrint.
If there are no more questions, let's thank the speaker again.
Okay.